Welcome to the deep dive. Today, we're going to tackle one of the, I think, biggest myths still floating around in tech.
Oh, I know this one.
It's the idea that front-end engineering is just, making things pretty with a bit of HTML and CSS.
Right.
If that's what you still think, you are basically operating with an architecture that's, 2 decades old?
At least. The modern truth is that the front end isn't just the presentation layer anymore. It's a really complex, distributed system, and it's running right inside the user's browser.
A distributed system.
Yeah, and it demands the same rigorous thinking as any major back-end infrastructure. We're talking about meeting demands for speed, scalability, reliability, and security.
For millions of users.
For millions of users, all using whatever resources they happen to have on their device.
And that's the critical shift, isn't it? So our goal in this deep dive is to kind of shortcut you past the basics and get right to the core architectural concepts that define this new reality. We're taking 21 critical system design choices from our source material and translating them directly into how they apply on the client side. Think of this as the blueprint for building web apps that can actually scale.
Let's do it.
Okay, let's unpack this, starting at, the very beginning. If the front end is a system, the first major decision you have to make is, it's the most foundational one.
Where and when the page gets built.
Where and when the page gets built. This is where the engineering really starts.
It is. This is the whole world of rendering and delivery models and this one choice.
Yeah.
It dictates everything about speed and how fresh your content is. Let's start with the one that gives us the most predictable performance.
Okay.
Static site generation, or SSG.
SSG, the name kind of gives it away, right? Static.
It means the entire page, the HTML, the CSS, all of it is fully pre-built at deployment time. It's like preparing all your API responses and templating way in advance.
So the system queries the data, builds the output, saves it as a file.
And that's it. So when a user makes a request, it doesn't trigger any computation. They're just downloading a pre-baked file.
Which means it's fast.
The benefits are massive. You get phenomenal speed because there's no runtime generation, near infinite scalability because you're just serving simple files from a CDN, and fantastic SEO because the HTML is fully formed right away.
But the downside is pretty obvious.
Yeah, if you change a blog post title, you have to rebuild and redeploy the whole site. It's perfect for stable content, like documentation or marketing sites.
But that model breaks down so fast if your content is dynamic. Let's say you run a huge e-commerce site. The product descriptions are perfect for SSG, but the prices, they might change every hour.
You're not rebuilding the entire catalog for one price update. That's just a massive operational headache.
Yeah.
And that operational friction is exactly why incremental static regeneration, or ISR, was created. It basically lets you have your cake and eat it too.
Okay, how does that work?
The pages are still pre-built, but you attach a revalidation timer to them. So when that timer expires, the next user who visits gets the old, instantly served cached page.
So they don't wait.
They never wait. And in the background, the system silently triggers a rebuild of only that one page.
Ah, that is a crucial system design insight. You're optimizing for speed and content freshness at the same time.
That's it. But then, if your data is truly personalized or real-time, like, say, a user's bank statement or a live admin dashboard, you have to move to server-side rendering, SSR.
The traditional model.
The traditional model. The page is built on demand for every single request.
It guarantees freshness, but the trade-off, I'm assuming, is resource load on your servers.
Absolutely. Under heavy traffic, your servers are just constantly generating pages, which can introduce latency. And then you have the final one, client-side rendering, or CSR, which flips the computation entirely.
Okay, so the server just sends an empty shell.
A bare minimum shell and a bunch of JavaScript. The browser downloads the JS, fetches all the data it needs, and then builds the page locally.
Which makes sense for those really rich interactive apps where you stay on one page for a long time, like Figma or Google Docs.
Exactly. But you pay that cost up front. The initial load time can be pretty slow.
So the most interesting concept here really is hybrid rendering, because in reality,
No one uses just one.
nobody uses just one. Almost every scaled application is a mix.
A mix of all four. Your marketing pages are probably SSG, your product listings ISR, your user dashboard is SSR, and your little chat window in the corner is CSR. The architecture is about choosing the right model for the right job.
That's a great way to put it. And once you decide how to build it, you have to get it to the user fast.
Which brings us to CDNs and Edge Delivery. A CDN is simple enough. It serves your static files from a server that's physically close to the user.
But edge rendering is the next level.
It's the next step. It's running actual code, maybe even those SSR functions, at that edge location. You're pushing computation, not just files, as close to the user as you can possibly get.
All to shave off those milliseconds of network
Because
latency.
every millisecond counts.
Okay, so we've handled the initial delivery. Now let's shift from architecting the build to actually measuring the user experience, because you can't optimize what you can't measure, right?
And this is where we need to think about web performance metrics, kind of like how a back-end engineer thinks about server latency. The first is TTFB, time to first byte.
How quickly you get that first chunk of data.
Right. But the most critical one for the user is LCP, largest contentful paint.
That's what they actually see.
That measures when the main meaningful content, the hero image, the big headline, fully appears on the screen. If your LCP is slow, users are gone. They just abandon the page.
And we absolutely have to talk about the one that drives everyone nuts.
Yeah.
The shifting page syndrome.
Yes, that's CLS, cumulative layout shift. This measures page stability. If an ad or an image loads late and pushes all the text down just as you're about to click something,
It's the worst.
it's deeply frustrating. And these shifts aren't just annoying. They interrupt a person's cognitive flow. We should be monitoring CLS as rigorously as a back-end error rate.
So we know what to measure. How do we start optimizing the payload without just cutting features?
You start by not loading things until they are absolutely needed.
Lazy loading.
Lazy loading. It's essential for managing heavy media and complex components. You only start loading those big assets images way down the page, components inside a hidden menu, when they're about to enter the user's viewport.
So if you've ever used Instagram or Pinterest, that infinite scrolling feed.
That's all lazy loading. It's the only way to keep the initial page weight down.
And what about repeat users? How do you make the experience feel instantaneous, even on a bad connection? This is where service workers come in.
Service workers are they're game changers. You can think of them as a personal proxy server that runs inside the user's browser.
A proxy server in the browser.
Exactly. It runs in the background, and it intercepts every single network request. It can then decide whether to go to the network to get the resource or just serve a cached version instantly from the device itself.
That is so powerful. It basically turns the user's device into its own little web server for your app.
And that guarantees instant load times for repeat visitors and enables that key reliability feature, offline mode. They're the backbone of any app that wants to feel as stable as a native app.
Okay, so this is all about serving the page fast, but none of it matters if the data layer underneath is a mess. Let's pivot to the next big choice, data management and API strategy. Where does data even live on the client?
Well, we can define three crucial tiers of what we call state management. First, there's the temporary component-level local state.
Like, is a drop-down menu open or closed?
Exactly. Then there's global state, which affects the whole app, like the user's theme preference, light mode or dark mode.
Yeah.
And then there's the server cache. And this is arguably the most important one for performance.
The server cache. That almost sounds like having Redis in the browser.
It is, essentially. It's client-side storage of frequently used API data. By storing this, you avoid making the same network request over and over.
So if I click back to a product page I just saw.
You don't hit the API again. You just hit your local cache. It makes the app feel incredibly responsive.
Speaking of APIs, the source material puts a really strong focus on GraphQL. What's the problem it's trying to solve that traditional REST APIs don't?
The technical problem is overfetching getting back 10 fields when you only needed 3. But the organizational problem is dependency and friction.
What do you mean?
With REST, if the UI team needs a new piece of data, they have to go ask the backend team to build or change a specific REST endpoint for them.
Which means meetings, coordination, delays, cross-team friction.
Right. GraphQL shifts that power. It gives you a single, flexible endpoint. The client team, the front-end developers, can now query for exactly what they need in one trip. It lets them deploy UI changes without being blocked by the back-end release cycle.
It's a velocity thing.
It's a massive velocity thing. It's a genuine system design decision.
Okay, and for handling huge lists of data like social feeds, we need smart pagination. Why is the classic page number approach so unreliable for live data?
You mean offset pagination. Give me page 2, then page 3. It works okay for static data, but imagine you're scrolling a live feed. If 10 new posts appear while you're on page 2,
the whole list shifts under you.
It shifts. And when you ask for page 3, you either see duplicates from page 2 or you miss some posts entirely. It's just not reliable for dynamic systems.
So you need a bookmark.
Precisely. That's cursor pagination. Instead of saying, give me page 3, you say, give me the data that comes after this specific item ID. That ID acts as the cursor. It guarantees consistency.
And if we need true real-time updates, not just fetching, but pushing.
You have two major tools. First is WebSockets. That's a bidirectional, persistent connection.
For chat apps, collaborative editing.
Right. And the second is server send events, or SSE. It's simpler. Just a one-way push from the server to the client. Perfect for things like notifications or stock tickers.
All right, moving to our final segment. Scaling the development process itself. Because if we treat the front end like a monolith, we're setting ourselves up for failure as the teams grow.
This is where we see large enterprises turn to micro frontends.
So just like microservices on the back end.
Exactly. You break the big application into smaller, independently built and deployed sub-applications.
So if a company like Spotify has a player component and a playlist component, those are actually different teams deploying separately.
Yes, they can develop in parallel, maybe even use different frameworks, and deploy on their own schedule. They get composed together at runtime, often using tools like Webpack's Module Federation to share common code. It eliminates those development bottlenecks.
And that independent cycle makes CI/CD, continuous deployment just as vital for the front end as it is for the server.
Oh, absolutely. The pipeline isn't just about compiling code. It's automated testing, safe deployments, rollbacks. It's the only way you can deploy constantly without breaking production.
We mentioned reliability with service workers. Let's touch on progressive web apps, PWAs, as the kind of ultimate goal for reliability.
PWAs use those service workers to let a web app be installed and behave almost like a native app. This guarantees an offline-first experience. If you lose connection, the core UI and your cached data are still there.
So for companies targeting places with shaky mobile service, like Twitter Lite.
It's non-negotiable for user trust.
And finally, reliability is nothing if the system is vulnerable. Frontend is the first line of defense. What are the key threats we have to mitigate right in the browser?
The browser is a hostile environment. So first you have to mitigate XSS, cross-site scripting, by sanitizing any user-generated content so they can't inject malicious scripts.
Right.
You need strong token management to prevent CSRF, cross-site request forgery, and most importantly, you need a strict content security policy, or CSP. That tells the browser exactly which domains are allowed to run code, shutting down anything unauthorized.
And when all this complex architecture, inevitably fails, because all systems do.
You need observability.
Front-end observability.
This is tracking client-side errors in production. Using a tool like Sentry to capture JavaScript exceptions and connect them back to the user interactions that caused the crash. It's the front-end version of monitoring 500 errors on your server, but you get more context.
What page were they on? What device were they using?
Exactly. You can't fix an error if you don't even know your users are experiencing it.
This has been, wow, deeply fascinating. The core takeaway, to sort of synthesize all of this, is that modern web development requires front-end architects to stop thinking about presentation.
And start thinking about distributed systems.
Distributed systems, performance budgets, caching hierarchies, and how to scale the organization itself.
Right. And if you're building or analyzing a system today, you need to leave with these three, foundational questions. First, where should the computation happen? Is it cheaper, faster, or more reliable on the server, the client, or at the edge? Second, how do we scale this? Can the current design handle a 100x traffic spike without crushing our budget or performance? And third, and maybe most critically, how do we maintain this? Are we building a cohesive system that lets teams move quickly on their own? Or are we just building a tangled monolith that's going to slow everyone down? Those are the long-term architectural implications.
Treat the front end with the respect it deserves, and you'll build better products. Thank you for joining us on this deep dive.